Nobody is there. What to say? Nobody is there. Hmm? Only Bharti madam is there.
Currently 4 years.
Oh, 4 are there?
You can start your question.
Can I see 4 those? Can I see 4 those? No? No. Participants are not seen here.
More questions for staff.
पार्टिसिपेंट्स का नाम देख रहा हूँ मैं. पार्टिसिपेंट्स का नाम
नाम
नहीं साइड में नहीं आएगा.
हाँ.
Oh, okay. Yeah. Hello. Good evening, everyone. So, how are you people doing? So, you have any questions to begin with? So, if you have any questions, please write on chart board. So, let me start discussion on those things. Hari Keshwanaran is around? If you are there, say yes on chart. So, you have asked a question. So, let me answer that one. Yeah.
No, sir. Because it is, sir.
Yeah. Can you go back to here? This. Oh, this is here.
No, sir.
No. Yeah, they're not here, right?
No. Gmail.
Okay, the question is, okay, what was your answer? I mean, the answer for that, yes, I think this one, there was a mistake, okay? And, the right option was not there in that one, okay? So I did talk to TAs, and then I think we will be giving a mark, or that mark will be cut for everyone, because the right option for that one was missing, okay? Treatment of palladium chloride with HCl to make it H2PdCl4, okay? Why we make H2PdCl4 is to make it soluble, okay? And then it is treated with cod to form PdCl2 cod. So that option was missing in this one, okay? So that marks will be given. Don't worry about that one. The correct option is missing. The correct option should be PdCl2 C8H12. That should be, okay? That option is missing, okay? Yeah. Okay. Yes. NO. If you just look into the molecular orbital diagram, okay. So let me. Okay, it has 11 electrons. Right? 6 are from carbon, 5 are from nitrogen. So 11 electrons are there. In oxygen O2, we have uh, 12 electrons are there. So as a result, what have we have 2 electrons in the antibonding orbital, and they are singly occupied. As a result, that is paramagnetic. In the same way, if you see NO has 1 electron less compared to O2. So that 1 electron sits in the antibonding orbital. Okay, so when you remove 1, the bond order becomes 3. As of NO has bond order of 2.5 because 6 electrons are there in the bonding orbitals and 1 electron is in the antibonding. So bond order is 2.5. So by eliminating 1 electron present in the antibonding, by making a nitrosyl cation, it becomes bond order will become 3, it becomes stronger. So that electron goes to the metal when it becomes cation. So in that case, what happens? It becomes 1 electron donor. But you should remember, when it establishes a bond with metal, there should be 2 electrons. That means it almost looks like electrons are shared between metal and nitrogen. 1 electron comes from the nitrogen and 1 electron comes from the metal, so that we have metal to nitrogen bond. It appears like NO minus actually. Okay, when it acts as a 2 electron donor or 1 electron donor. Then when it is 3 electron donor, 1 electron in the antibonding plus lone pair on nitrogen goes, it becomes 3 electron donor. That can happen only when NO bond and MNO we should be linear. Okay, if not, if it is bent, what happens? The lone pair will be perpendicular at uh, orthogonal to metal orbital. As a result, what happens? There won't be any overlapping. So it is bent. Okay, so let me show you on a so writing all this.
Please,
Hmm.
possible share.
Sure. So just if you see here, NO, as I mentioned, uh, if you just take here N is 5 electrons are there, oxygen 6 electrons are there. If you just go to your Lewis dot structure, so this 1 electron will be there and this will be sitting in the antibonding orbital, pi star. Okay, so then when it becomes NO plus, and this is gone, and then it becomes simply this one. Now, this is already given 1 electron to the metal because it is now NO plus. And then when it establishing a bond, okay, so it forms a bond like this here. Now, metal also has to give 1 electron. That means it appears like it's NO minus actually. Okay, NO minus. Okay, so NO minus has 2 electrons that is coming, but it's not the case. But when it is 3 electron donor, it should be something like this. Okay. Now this also comes here. In this case, what happens? This will be something like this. This bond will be something like elongated. So this is how you can explain. So we call it as 3 electron donor or 4 electron donor. 3 electron donor or 1 electron donor. Okay. When 1 electron donor, it is NO plus. And of course, lone pair is intact and 3 electron donor. So this one. Okay. And but when it is 3 electron, it is giving, you should remember that the 4 electrons are participating in establishing a bond between metal to nitrogen. Okay. Because 1 electron, when it gives, it's not sufficient to establish a bond. Okay, metal has to give 1 electron, so it becomes 2 electron bond. It's almost like CH3 dot giving 1 electron to the metal and establishing a bond. Now, when metal to carbon bond are establishes, okay, then again you have minimum of 2 electrons. So it becomes almost like it appears like CH3 minus. Okay, so this is how you can explain. Is it clear for you? So that's question number 10 in assignment 5 is anyway reevaluated and, that is discarded. So don't worry about that question. Any other question now? Is it clear about NO? Arup? Oh. Mhm. No more questions, sir? Any more questions are there? No? Not. No. Any more questions are coming up? Questions have you?
Sir, proceed to the question.
So if any other queries are there, please go ahead and write so that I can answer. Arup, is it clear for you? NO? And it's little bit looks like complicated when you go for both ionic and covalent method for counting electrons, especially when you have NO, but you have to be very careful. Okay, once when NO become NO plus, okay, and then metal, one electron should be added. Okay, and then you should not count any electron from the NO. But later, when you go for ionic method, you should consider 2 electrons for NO, so that 1 electron would be less for metal. This is how you should count. Yeah. Yes. Yeah. This question, yes. One of the option, as Gnanarajan suggested, yes, it should have been CO only. That only is missing. In the absence of that term missing, okay, and even that becomes a correct answer. So that we'll correct that also. Although we are getting both CO and CO3, okay. That question, that means individually, if they say one of the product is CO, yes, it's absolutely correct. That option should have been written properly. So if somebody writes that, mark will be given for them also. Okay. That's also a correct option. So it's not an incorrect option. You got it? Yeah. I will write. I will write that equation. Okay. So we are taking this dianion So this is very similar to Na2FeCO4. We have discussed it on a couple of occasions. Okay, this is on treatment with two equivalents of carbon dioxide, forms Ru2CO8 minus plus CO plus CO3 2 minus. Okay. This is a dimer. And this is very similar to like we saw in case of other reactions where Me3NO abstracting CO, okay, plus CO gives Me3N plus CO2. So this is another reaction very similar to that one. CO3 comes out here. Okay, when oxygen is abstracted from CO, so other CO is added now. That means reduction of CO2 takes place. Okay, reduction of CO2 takes place, and that results in the formation of CO2 becomes CO3. Okay, so that means we have taken two equivalents of carbon dioxide. One of the carbon dioxide is getting reduced. Okay, so thereby results in the oxidation of another one to form carbonate. Okay, these kind of reactions are quite common with carbonyl complexes. Okay. The mechanism I had showed for trimethylamine N oxide, in the same way there, what we do is we do oxidation of carbon monoxide into carbon dioxide. Here we are doing reduction. Okay, in that case, CO2 becomes CO. Other one abstracts, it becomes CO3. I will post you a detailed one in my next mail. Maybe tomorrow or day after tomorrow, I will post you that one so that you can have a look at it. No. Any more doubts or clarification is needed? From January 2024, so I am coming up with another course that is about interpretative spectroscopy. Okay, so here 4 very basic spectroscopic methods which are very essential for synthetic chemists, biochemists, and people who are working in pharmaceutical industries will be discussed. That's about interpretive spectroscopy. That includes NMR, multinuclear NMR, IR, UV visible spectroscopy, and also spectrometry. And I'm sure you will all enjoy that course, and it's very informative, and I'm considering a lot of examples, and I'm also taking reactions, and also one can monitor reactions and how to get some insight into reaction mechanism, and also how we can get information about the need to change the reaction if you are getting more than one product. All those things will be discussed in that one. So hope you will all join that course when it starts in January 2024. It is very useful for you people. If you want to appear for GATE, JAM, or CSA or examination, or if you're doing PhD, this is quite helpful for you people. So, yeah, if there are no questions, okay. Is there any concept in lanthanides and actinides, or it is only for transfer? Well, lanthanides and actinides, what happens? Yes, we are. Well, there also you can talk about HOMO and LUMO using ligand field theory, but it's a little bit complicated because we have coordination number more than 9 invariably comes. And also, if you just look into the examples I have shown where we are using, especially for coordination number more than 9 in the table I have provided while discussing valence bond theory and its application to transmetal complexes, I have shown some compounds where F orbitals are utilized. So CFSE, you can talk about CFSE, but it's less pronounced when you are looking into those things. And mostly the geometry that we are going to assign and all those things are decided by kinetic aspects, that is the bulkiness of the ligands and all those things. So you cannot really, directly apply CFSE to determine the geometry in those cases. However, we can use it. Okay, I wish I had some time to discuss about lanthanides and actinides as well, but I do not. I didn't get time in those things. But it's more pronounced with 3D, 4D, and 5D metals. That I can say. And also, of course, you know that UV visible spectra, if you look into it, electronic spectra, they are all very sharp there. In case of lanthanides and actinides, we do get very sharp absorptions. And in the course that I'm presenting, probably I'll be considering some examples taken from lanthanides also while discussing UV visible spectroscopy. Okay. But Christofield theory is tailor-made for constant metals, and of course, it's not a complete bonding concept. That's the reason we use very effective and useful and informative and complete theories such as ligand field theory. And ligand field theory is nothing but molecular orbital theory, I would say. Yeah, when I update this course a couple of years later, maybe I can include some discussion of one or two lectures, about CFSE and its consequences in lanthanide and actinide compounds. Okay. So any other query? Gyanaranjan? Yeah. Okay, then see you all in my next live session. Thank you.